there. We're continuing our study of priority queues, and really this is a kind of case study where we've looked at an idea of a priority queue where you can test if the structure is empty, add to it, find the minimum value, and remove the minimum value, and those are the only four operations that we wish to run on our priority queue, and therefore we can optimize for those four operations. And so this has become a sort of case study in what data structures do we have and what are their running times as we apply them to these four operations. And let's see what we've got here. We tried representing it first using an unordered dynamic array, and if you're a Java person, a dynamic array is an array list. If you're a Python person, a dynamic array is just a list. And in general, it's a structure that lets us access elements in the middle in constant time by index and add to and remove from the end in constant time. So we used an unordered dynamic array, and that gave us pretty good time for add. We could add in constant time because it didn't matter where we add it, but finding the minimum and therefore removing the minimum took us linear time because we had to find the minimum. We had to look through all the elements. So the more clever thing we did was that we kept track of the index of the minimum. Where can we find the lowest value? And that gave us really nice times. Constant time to add, constant time to find the minimum since we knew where it was, but linear time to remove it since we would have to search through and find the new minimum in order to update that index. So there was some work in order to maintain this extra bit of state, the index of the minimum. So that was our winning representation, and then we introduced what if we wanted to improve upon that by keeping the array in increasing order. And so we tried that. But that actually seems to have killed us because not only did we get the same times for peek min and remove min, but we got linear time for adding. And the reason we got linear time for adding is that, well, now we have to add the element in the proper place. That involves shifting the elements over to make room for the new value that we're inserting, since we're trying to maintain increasing order. And removing the minimum also involved shifting. We found the minimum in constant time. It's always the first one, but then we had to shift everything down. And we noted it's kind of unfortunate that every time we remove the minimum, we're always removing the first element, and that requires us to shift all the elements to one position to the left, which is a linear time operation. And so our hunch as to how to speed this up might be, well, if removing from the front is the thing, if removing is something we do often, and removing from the front is slow because everything would have to shift down, maybe we can change the situation so we're always removing from the end, from the back. And that would mean, if we were trying to remove the minimum, that means that our dynamic array should be stored in decreasing order so that the minimum is always at the end. Let's see if that intuition pays off for us. So, representation number 4. And don't think we're out of the woods yet. There's going to be a lot of these. I don't think it's super important that you understand that these aren't a bunch of representations you need to memorize or anything for your course, but they are an excellent example of practicing what it means to propose a data structure and analyze it in terms of its big O running times. So representation number 4, another one of these dynamic arrays, another array where we can add and remove from the end, but this time in descending order. So pretty much the same picture as before, but this time I believe our data values from before were 2, 3, 5, 8, so if it's in descending order, they would be stored in the order 8, 5, 3, 2. Excuse me, getting over a cough here. And again, we'll look at those 3 operations and figure out how long they take to run. Move min. So, how long to add if it's in decreasing order? Well, it's exactly the same problem as before. We need to shift the elements to maintain the order. So when we add, let's say, 4, that means we need to shift 2 to the right, and 3 to the right, and 5 to the right, and now we've made enough room for 4. Therefore, looks like it's linear time because of the shifting. By the way, notice I keep indicating why we're getting that particular running time, and I think that's really the key here. You may be in a course where your tests often consist of indicating whether something is constant or linear or what have you, but the key to understanding it isn't whether you got the time right, it's why, what's contributing to that time, and here it's the shifting to make room so that we can maintain the order. Right? Shifting maintain the order. Okay, how about peeking at the minimum? How long does it take to find the minimum? Well, where's the minimum? If it's in decreasing order, it's the last element, and because I know this is one of these, let's label my indexes 0, 1, 2, 3, 4, because it's an array, I can access any element in constant time, including the last one. Therefore, constant time to find the minimum. Just return the last value. And so far this is the same running times as we saw with increasing order, but the big payoff ought to be in decreasing order if our hunch was correct, or in removing the minimum in decreasing order. So, to remove the minimum, what do I have to do? Well, I know where it is. It's at the end, and I know how to remove it. I remove it by simply removing that last box, and because this is a dynamic array, such as an array list in Java or a list in Python, removing the last element can be done in constant time. Therefore, since that's all I have to do in remove minimum is remove the last element, remove the last, we're going to have constant time. So, let's review where we're at here. In the first representation, we had linear time for 2 of the operations. In the second one, we got it down so that only remove min was our slow operation, and we could add and peek at the minimum in constant time. That was where we kept track of the index of the minimum in an otherwise unordered array. In our third representation, well, we had 2 linear times. But in our fourth representation, this dynamic array in decreasing order, only add was linear time. So, our winning representations seem to be 2 and 4. Either keep it in no particular order, but remember where the minimum is, in which case removing the minimum will be slower, or keep it in decreasing order, in which case adding will be linear time. And so an important question is, which of these is better? Would you prefer that add be fast, or that remove minimum be fast? If you think about it, in order to remove, I must have already added. Therefore, the number of times that I run the add operation must be at least the number of times I run the remove minimum operation. All right, let's make a note of that. That seems important. Number of adds must be greater than or equal to the number of times we used remove min. And for that reason, we might feel that the running time of add was more important. Let's continue that thought. Therefore, more important that add be efficient. So, order 1 add and order n remove min is the best so far. And what gave us order 1 add and order n remove min? That was our unordered, so that was representation 2, unordered dynamic array with index of the minimum. So that seems to be winning. I should point out that we might find ourselves in a situation where we have lots of time to do the adds. The adds happen all up front, but the remove mins happen at mission critical moments during space shuttle launch or something like that, in which case maybe we do prefer this way, representation 4, where adding is slow, but we can remove the min nice and quickly. But if we're concerned that we're probably going to add more than remove min, we should probably stick with representation 2. So far that's the winning representation. Let's consider a different approach, though. What if we use a linked list? So, representation number 5. What if instead of arrays, we tried a linked list? And let's do an unordered linked list. Linked list where the data is in no particular order. Is that a good idea? Check my notes for a second. Actually, I think we can agree that that's probably not going to be the winning. So we could go through that, but let's stick with what I think are the 2 best ways to use a linked list. Linked list in increasing order, and then afterwards we'll try representation number 6, which will be our final way of representing the structure using traditional things like dynamic arrays and linked lists. Then if we want to get fancier, we can get into the world of trees, and ultimately we're going to discover that a binary heap, a minimum binary heap, is going to be our best data structure for solving this problem. But before we get to that, linked list in increasing order, and our last one will be an unordered linked list, but with reference to the node with the minimum value. And I'm sure there's other ways we could use linked list, but I think these are two are going to do the best. So before you start the next video, you might stop and think about what are going to be, let's make some room for these, what's going to be the running time of our three operations, add, peek, min, and remove min, for each of these scenarios. And when you think you have a feel for it, and you have a preference maybe between which of these you prefer, start up the next video and we'll take a look at the answer. I'll see you there.